So this is a really, really important and also kind of challenging lesson that we're about to tackle right here. In 3.2c, we're going to learn about two new kind of measures that we can use to decide how good of a job a least squares regression line is doing. We're going to learn about something called S, and we're going to learn what that R squared that we've talked about a little bit that we see on the calculator, what that's actually good for and where it comes from. So this is definitely a lesson you're going to have to probably pause, maybe replay parts of this video to make it make sense, because it is a lot of kind of challenging content right here. So stick with it and make sure you really kind of dig in to make sure it's making sense. So our big problem for the day, the context to wrap your heads around, is that soda problem from earlier on. I think it was section 3.2a, where basically what we were doing is we were looking at how long we tapped a can of soda after it had been like shooken up. And then we were going to look at how much soda was left after we opened it. And we saw that there was a pattern between cans that were tapped for longer having more soda remaining. Now, that was good, and we talked about it already with line of best fit, and life was great. But we want a way to be able to talk about like the different sized errors for each of these points right here. So if we look, when we're looking at a line of best fit, we may want to look at like, well, how much was this point off by versus how much was this point off by versus how much was this point off by, to get a sense of like what a typical residual size is. This is going to sound a lot like the idea of standard deviation. Standard deviation was typical distance from the mean. Well, what we're going to look at here in this lesson is the standard deviation of the residuals, how far off each of these dots is right here from the line of best fits. Okay, so being able to find a standard deviation for a typical distance to the line, just like we used to do typical distance to the mean. Now, you're going to run into a similar issue that we got with standard deviation. We've kind of referenced it a couple times in this chapter already, but if I were to take all these residuals straight up and just add them, I have positive residuals and negative residuals that are basically going to wipe each other out. So I have to do a very similar process to what I did in chapter 1 with standard deviation. Okay, so we're going to do a similar process, and there's a formula that I'll show you guys, but it's basically a way of taking all those residuals and coming up with an average or typical distance from that line of best fits. So the formula right here is kind of crazy, and it's at the bottom of the page. This is not a formula that I will ever make you guys use in AP Stats. Most of the time, what's going to end up happening is the technology is going to give us what the standard deviation is, and we're going to use it to analyze a problem. But I want to at least point out where the formula comes from and what it's doing, because it is similar to standard deviation that we've already talked about. If you look inside of the parenthesis in this formula, you have yi minus y hat. Yi is your actual y value, minus y hat is your predicted y value. So this parenthesis right here, actual minus predicted, is exactly what a residual is that we already learned about. You're going to take your residual, you're going to square it, that way they're all positive quantities and the positives and negatives don't wash each other out. You're going to add them up. You're going to divide by n minus 2 instead of n minus 1. It's a 2-variable problem, so there's more reason than that. You don't really need to know why. And then at the end of the day, we take a square root. So this very much mirrors the process we used in chapter 1. Okay, so that is how you would basically calculate mathematically the standard deviation of the residuals. And as it says at the bottom there, this value gives the approximate size of a typical prediction error. And a residual is a prediction error. It's how far off we were. The variable we're going to use for the standard deviation of the residuals is just S. We've used S in the context of regular standard deviation, but usually then it's S with a little X on it. Straight up S in a LinReg problem is the standard deviation of the residuals. Okay? So I will not make you calculate this whole formula for a set of data points because that's just crazy. But this problem right here is a little bit contrived, but it at least gets you guys a sense of how the formula would work. So in the soda example, we had 40 cans of soda, and the sum of the residuals squared was 951.536. When I say this is a little contrived, the sum of the residuals squared is like literally the numerator in this formula. So they're already telling you this whole complicated, ugly to find part is just that 951 number. So all I would do with this is I would still need to do these square roots. And my top is that 951.536. I would divide by my sample size minus 2 in a bivariate problem like this. So I'm going to divide by 38, and then I would just end up doing a square root on that. I've got new batteries for my calculator, so you guys don't have to watch me do this on a phone anymore. And it looks like when I actually calculate this right here, your value for S is a little over 5. It ends up being like 5.004. What does that number mean? What does S equals 5 basically tell us? Well, remember, S is the typical residual size for this problem. A residual is how much your predictions are off by on average. So there will be a little script that I give you formally later on in these slides, but for now, let's just kind of talk through this. When we use our LSRL to predict soda remaining using tapping time, our predictions will typically be off by about 5.004. And remember, this is measuring a residual. When you do this, the typical residual size, residual shares the same units as your Y variable. So we're off by about 5 milliliters when we make a prediction. Some of our cans, if I were to go back to that, I'll go back real fast. So if you're still writing this, you can pause me. But if we look at our line of best fit from earlier on, some of our cans are going to be off by more than 5, like 6 or 7 off. Some are by less, some are dead on. If you average all those distances together, on average, those points are about 5 away from the line of best fit. That's what S does for us. How far on average will our predictions be off? So if I'm making a prediction about a new soda can that I just shook for however long, or tapped for however long, I can expect that my prediction is going to be off by up to 5 in either direction. Okay, so that is S. So the second portion of this lesson is on R squared. And actually, let me look real fast. I'll probably do a second take with this video here. So I didn't give an actual spot for the script, which I wish I had on these slides here, but I can just diagram this and then I'll pause and shift gears. So when we use our LSRL to predict Y using X, our predictions will typically be off by about, and this is S. This chapter, chapter 3, is very script heavy. When I ask you to interpret S or the slope of the least squares regression line or whatever, there are little scripts that I'm giving to you guys that help you figure out like how to wrap your head around it. So this is a script for S. And I'm going to go ahead and pause and regroup to talk about our second topic, which is a little more in depth, called R squared. Okay, so we're shifting gears now from S, which we just talked about, to the second way of telling how good of a job a line of best fit is doing, which is R squared. And S is actually the less kind of crazy of the two, I think, because we've already understood standard deviation. So this new concept of standard deviation of residuals is not so bad. R squared is kind of crazy, and it takes a little bit of a lead-in for me to be able to show you guys what it actually measures. So this is going to kind of attempt to set the stage for what R squared does for us. So I need you guys to picture, we're doing this problem where we tap the cans of soda. And I want you to picture like a couple of you were doing this project in my classroom. So there were 2 of you who were in my classroom doing this project, tapping cans of soda, opening them up and stuff like that. And say you were writing down all of your data in a little table. I wrote down a couple of the points that were in that chart from earlier. But you have a big table of data on the board. You've got all these cans of soda going on, and then you just leave my room a mess. So you just leave. And then I walk in afterwards, and after I get over my initial why is my room a total mess, I look at the cans of soda. And let's say I walked into this room where you guys had all your cans of soda out. Some had been tapped for 0 seconds, some for 8, some for 12, whatever. And they have the soda that's in them. And let's say I just walked up to a random can of soda, and I'm like, I wonder how much soda is going to be in this, like, not see-through can. So basically, if I wanted to make a prediction for just a random can of soda sitting on the table with all the other cans, I was not there at the beginning of the experiments. So I would not know how long that can was tapped for. So if I walk up to a can, I don't know if it's like one of those 0 second cans that only has like 245 left, or if it's an 8 second that has 270. If I just had to make a prediction for, like, I think there's this much soda in the can, what I would probably end up doing, because I wouldn't have access to the tapping info right here, like if I see a can, I wouldn't know what the X was, I would basically decide to just average these numbers to get my prediction. So say these average out to about 255. Well, I think that can has about 255. That can has 255. That can has 255. If you don't actually know the X value that goes with the cans and you're trying to make a prediction, a line of best fit isn't helpful because you have to be able to plug in X. So what I would do instead is I would just straight up guess the average every single time. So if I did not know how long the cans were tapped for here, I would just use Y bar. So Y bar is the average of your Ys every time. So if I didn't know how long the can was tapped for, I'm not going to be able to get any sort of special insight on this problem. All I'm going to do is just guess average every single can. That can's 255. So is that, so is that, so is that. What piece of information would be most helpful in making a more accurate prediction for how much soda is in the can? Well, how long it was tapped for. So how long it was tapped for, which is X. If I don't know X, all I can do is average these numbers and just guess that. If I know the X, that's really helpful. Because if I can see, like if they labeled the cans, oh, this was a 0 second can, well, probably a little less soda in that can. Oh, this was a 12 second can. There's probably more soda in that can. And if I know the tapping time, that can guide me in how I make my predictions. So knowing X would be a helpful thing. So again, this is a little bit out there, but I'm trying my best to kind of make it more understandable. So stick with me here, pause me, rewatch this, make sure you've got your head around that piece of the puzzle. So these two pictures right here need to show you what they're talking about. The dots in the picture are the same dots that we had way back with the scatter plot here. They're the same dots as earlier on. The only difference is in what we do for our predictions. In this first picture, this blue line is the average of all the cans. So that's me walking in the room, seeing the table, and just averaging those Y values. And basically, I wouldn't know how much the can was tapped for, so I would just straight up guess Y bar for every single can. Looks like the average of all the cans in the study is 265-ish. So I would be like, oh, that can's 265. So is that, so is that, so is that. You can see, like, look at how my predictions did when I just straight up guessed the average. I have some cans, like in the middle here. This can, I did a pretty darn good job. It's real close to what it was supposed to be. Same with this can, not off by too much, not off by too much. But I did a pretty dreadful job on cans like this one over here and this one over here. So you look at all these squares right here. The sum of all of those squares is written down right here, which is about 6,500, okay? That number by itself doesn't mean much, but that's just basically like, picture that 6,500 as like the sum of the square of my errors. So I want that number to be small. Small is good. It means my predictions aren't off. Big means I was off by a lot. And you can see these numbers over here, these giant squares, ballooned up this number right here. Okay, so that's the first picture. I just straight up guess average. The second picture, now I know how long the cans were tapped for. So instead of having to just guess the average every single time, I can actually use my line of best fit because I know X now for each can. So if you look at this red line versus my last one, this line, by being slanted, gets to go closer to the dots, especially over here on the end. This dot, which was a giant big old square like this in my last picture, is now a lot smaller because my line kind of went up to meet it a little more. Same down here, and even the ones in the middle are about the same size too. So if you look at the area of all of those squares in the greenish color, it's a much smaller number, 951 versus 6,500. So what I want to do is look at how much better the one situation is than the other. Okay? So this question here says, what percent of the variation is like the area of the squares, an amount of soda remaining, is unaccounted for by the least squares regression line? I have 951.3 like for the area of these squares. My predictions are still going to be off by this in some fashion. Okay? But they used to be off by this right here. This is a much worse situation on the left. So they used to be off by 6,506. And if I actually divide those, 951.3 divided by 6,506, it ends up being about 0.146. So that's 14.6%. So breaking this down again, all of that left picture is like my original error, off by quite a lot. This picture on the right, though, when I use my line of best fit, only has 14% of the bad stuff that it used to. Okay? So there's 14% of the bad stuff that we couldn't fix just by switching to that line of best fit. But then you can look at the flip side of that. If there was 14% of the bad stuff I couldn't fix, that means I must have fixed 86% of the bad stuff. So what percent of variation is accounted for? You would just do the complement on this, which is like 86%-ish. I guess 0.854. Okay. So if 14% of the bad stuff is still there, 85% of the bad stuff got accounted for by my line of best fits. My line of best fit helps me make much better predictions than just guessing the average. This number right here, this 85%, which admittedly is probably still a little like fuzzy and weird, and you're not really sure what I'm doing with it, this is what R squared measures. And I'll define it on the next slide, so we'll get right there. But conceptually, what you should think of, there are lots of reasons why my predictions for my soda cans may not be exact. Okay? One big reason is how much the cans are tapped for. So if I didn't even worry about how long the cans were tapped for, my predictions are all over the place. But over here on this second picture, I did account for that factor, the tapping of the cans, by using a line of best fit. So it took into account the fact that the cans were tapped for different amounts of time. But there are other reasons besides just how long you tap the can that would say how much soda is left in them. One could be how much soda started in the can. Maybe one can had a little more soda, so there was less airspace, so it just bubbled out more. Or maybe the temperature of the can was slightly different, and it was a little warmer, and that made more soda come out or less soda come out. Or maybe the metal in the can was slightly tighter, and you could just think about all these other maybes. Well, those are 14% of the variation in how much soda is going to be left. 85% was because of how long you tapped it for. So R squared, in a sense, measures what percent of all those factors, what percent of the responsibility is the tapping. And getting a big number like 85% means that tapping made a big difference in how much soda was going to be left. That's in a nutshell what is going on with R squared. So if that is confusing, and it very well still could be, you're not going to have to calculate R squared numerically. You're going to get it from a calculator, or you're going to get it from like a computer output technology deal. So I will not make you calculate R squared yourself like I did on the last page, but this is basically just a recap of how to find it. You take those squares. This guy right here is all the squares. You take all those squares, the sum of them, and then you subtract out from 1, and that gets you the percent of the variability you did account for. So what is the difference? Let me see if I did this on the next page before I talk about it. Yeah, I do talk about R squared versus S. So I'm going to save that for a slide or two. So S talks about your average size of prediction errors. R squared is just another way to talk about how good of a job your line of best fit does. And it talks about how much better the line is than just guessing the average for every single point. There's going to be a script that you can use for R squared, which is going to be one you're probably going to want to memorize. And after you memorize it and get used to it, you can kind of do your own, like I can put my own little spin on the wording and stuff, but I recommend until you feel really good about this, use this exact script and memorize it here. You're going to talk about blank percent of the variation in your Y. So the Y in this problem is soda remaining. It's accounted for by the linear model relating Y to X. So in our problem, we got that 85.4% number. Let's talk about what that means. And I've already done it in words earlier, but let me go ahead. I'm going to write it down. Well, I'll just talk through it as I go. We would say that 85.4% of the variation in soda remaining, and that's in milliliters, is accounted for by the linear model relating soda remaining to tap time. Out of all those things, the temperature of the can, the metal of the can, the amount of soda in the can, blah, 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 that could make a difference in how much soda bubbles out. 85% of that variability is accounted for by the line of best fit. Tapping time, 85% of the fix. The other 15% MIA from all those other factors is how you guys should think about that. Not an easy concept to wrap your head around, but really important in being able to fully analyze a scatter plot problem. So how is R squared related to R? It turns out that R squared is literally the square, the square of R. R is the square root of R squared. So in our problem that we just got done doing, 0.854 was R squared. If I wanted to know R, all I'm going to do is take the square root of that number. I would just do square root 0.854, which means that R is 0.924. When you square root a decimal, it gets bigger. So if I take a square root on both of these, I get R. Now you have to be careful when you do these. R squared will always be positive. It's a percentage. It's also something squared, so you're going to get a positive quantity when you do these. R could be positive, could be negative, but if you take a square root of a positive, your calculator is always going to say a positive number. So what you need to do after you take your square root is look at the problem. Way back when I started talking about this problem right here, this problem has a positive correlation. The points are going upwards right here, so my R is positive. If I would have had a problem where my scatter plot was going downwards, I would just tack a negative sign on my R at the end. So it's going to be positive 0.924 for this problem here. So you have to check if R should be positive or negative, and that just depends on the problem. How is R squared related to S? Both measure how good an LSRL is. When you look at the difference between them, though, they try to go about deciding how good the line is in two different ways. S talks about your typical prediction error. So S tells you for an average point, if I'm just a random point, how far am I supposed to be from my line of best fit? So it gives you more information about like the individual data points, and that's helpful in that sense. R squared is more of a holistic overall. So R squared is more of the overall variation in y that's accounted for. So this is more big picture. This is more individual points. So S is helpful if you care about individual points. This is more of an overall deal. And just like most things in statistics, guys, there's not like a one magical, just use this thing and everything is wonderful and it's all you'll ever need. Statistics is all about using what's at hand, using different tools to see if they point you in the same direction. So one is not better than the other. You need to know how to analyze and use both of them because they tell you two different things about your data sets. So we're going to go ahead now and practice on a fresh example. We have a data set with the number of points scored per game and the number of wins for 12 different college football teams. So this is kind of tying together. There's nothing new conceptually here. This is practice. We're going to look at this line of best fits, and we're also going to look at S and R squared and talk about those. So just by like the eyeball check, that line of best fit looks pretty decent. My data set, just by my eyeball test, looks like it's linear. It doesn't seem like there's a better model than a linear model. But you do not make that decision on your own. You use a residual plot to decide that, which is sitting over here. So on the next page, I ask you for a couple things. Is a linear model appropriate? Interpret S, interpret R squared. Is a linear model appropriate? You're going to say yes, a linear model looks appropriate because the residual plot shows only random scatter. There's no leftover pattern in your residual plots. So I'll pause and get that written down. All right, so there's the wording you would want for this problem. Anytime they ask you about a linear model being appropriate, use a residual plot. Do not just eyeball it. Do not get tricked into using R and being, oh, R is high, yeah. You have to look at a residual plot. The next thing we have to do is interpret S and interpret R squared. So when we look at S, remember, S measures your typical prediction error, average size of residuals, basically. So looking back at my scatter plot right here, I have some positive residuals like this guy. I have some negative residuals like this guy. Those tell you how far off your line is. My line was trying to predict wins for football teams based on the number of points that they actually have. So when I think about what that S of 1.24 is actually telling me, it's saying that my residual size is off by 1.2. All right, sorry, my phone keeps going off, so I have to keep pausing this. Looking back now, collecting my thoughts here, we're looking at S. S is 1.24. My Y units in this problem are the number of wins. S is the typical residual size. It's in the same units as Y. So S is in wins when we look at this problem. What it's saying is that our points are typically off by 1.24 wins when you average some that are more off, some that are less off. All right. Use your script when you write these out. Don't just try to freestyle it because you'll miss important parts of it. After you've kind of used the script and learned it really well, then maybe you can go with your own words. But I super recommend you guys just memorize those scripts for now so you can wrap your heads around what's going on. So when using our LSRL to predict wins based on points scored, our predictions will typically be off by about 1.24 wins. Our predictions would typically be off by around 1.24 wins. You need that extra context of like when you have X and Y and you're predicting Y based on X. So if you just say, oh, we're off by 1.24 wins, that won't be good enough for full credit. So learn the script, but that is basically what S is telling you. Last thing in the slides is R squared, and R squared is a 0.88 for this problem. Remember what that does is it tells you what percent of the variation in Y our line takes care of. So in our problem, we're talking about wins. There's a lot of different things that can influence your wins in a problem. I guess this is football right here. Like they're talking about points you score. Defense would be like the next biggest thing. How many points do you give up? I guess there are probably other factors too, like how clutch you are. I don't know, stuff like that. But 88% of the reason why you would win, or the variation in predictions from why you would win, is based on how many points you score. So again, just using our script right here, we would say that 88% of the variation in Y, so variability in Y is, oh, sorry, don't actually write Y, in wins is accounted for by the linear model relating wins to points scored. So there's a lot going on in this section, but hopefully you feel fairly comfortable about S and R squared, both really important concepts. So rewatch this video if you are still iffy on those different things, or come see me in class.